This is Group A6 on Project 7, Variance and Chebyshev's Inequality by Chris Hammoud, Aaron Ridenauer, Yujing He, and Ben. For the definition of variance, let x be a random variable on a sample space S. The variance of x, denoted by v of x, is v of x equals the summation of x of s minus e of x squared times p of s. That is, v of x is the weighted average of the square of the deviation of x. The standard deviation of x, denoted as sigma of x, is defined to be square root of v of x. If x is a random variable on the sample space S, then the variance of x is equal to e of x squared minus the quantity of e of x squared. To prove this, we need to note that v of x is equal to the summation of x of s minus e of x squared times p of s, and this is equal to the summation of x of s squared times p of s minus 2 e of x times the summation of x of s times p of s plus e of x squared times the summation of p of s. This is equal to e of x e of x squared minus 2 e of x times e of x plus e of x squared, which in turn is equal to e of x squared minus quantity of e of x squared.
So here is an example of variance. What is the variance of the random variable x, where x is a number that comes up on Faraday's rule? First of all, we need to find out the expected value for x, which is, by definition, 1 plus 2 plus 3 plus 4 plus 5 plus 6 over 6, which gives us 7 over 2. Now we can calculate the variance. It would just be, by definition, 1 minus 3.5. This is the value of 7 over 2 actually, squared, plus 2 minus 3.5 squared, plus all the way to 6 minus 3.5 squared. Whole thing divided by 6 again, because it's still the probability of the whole thing, and that will give us a value of 35 over 12. And here's another way of doing it. Now let's just erase them all. Okay, so now we can use the equation derived by Aaron, which is v of x equals to e of x squared minus e of x that thing squared. And considering we don't know e of x squared, we can just calculate it right here, which is be 1 squared plus 2 squared plus 6 squared over 6, and that will give us a value of 91 over 6. Now we already calculated e of x, which equals to 7 over 2 from the previous video clips. Now we can just directly calculate the v of x, which is 91 over 6 minus 7 over 2 squared, which would be 35 over 12.
Chebyshev's inequality states that if x is a random variable on a sample space S with probability function p, if r is a positive real number, then p of the absolute value of x of s minus e of x is greater than or equal to r, then that is less than or equal to v of x divided by r squared. To prove this, let A be the event that A is equal to x of s minus e of x is greater than or equal to r. What we want to prove is that probability of A is less than or equal to the variance of x divided by r squared. Note that the variance of x is equal to the summation of x of s minus e of x squared times the probability of s, which is equal to the summation of x of s minus e of x squared times probability of s plus the summation of x of s minus e of x squared times p of s.
Right, now for an example of how to use Chebyshev's inequality and some possible problems with the estimates that it gives. So if x is a random variable that equals the value of one die then we have from previous examples that the expected value of x is equal to 7/2 and the variance of x is equal to 35/12. Now, consider Chebyshev's with r equals 3. Then we have probability that x minus 7/2 is greater than or equal to 3, is less than or equal to 35 over 12 over 9, or 3 squared, which approximately equals 0.324. But we can easily see that because no die roll can be greater than 6, no single die roll can be greater than 6, we have that x does not equal any number x is no greater, so x is less than or equal to 12 12 halves or 6. So x can't be any more than 5 halves greater than its expected value, since 3 is greater than 5 over 2. We can see logically that since we can't get a die roll greater than 6, the probability that the absolute value of x minus 7 halves, the expected value, is greater than or equal to 3 does equal 0 in actuality. So while this is the correct answer, this is the estimate given with Chebyshev's inequality, which is not as precise.